Hey everyone, welcome to the lecture 3 of Winter School of Solana. Today we'll be talking about Solana programming model. So let's briefly introduce these lectures and the upcoming lectures going forward. So about this lecture, we'll be talking about a brief introduction to Solana programming model. That means making a brief overview, talking about accounts and transactions. And those are pretty much the basic core concepts that we need to know to start up our programming journey on Solana. We'll also be doing a hands-on example, which means setting up a new Anchor project and then writing your first Solana program in it, which will be a calculator, and we'll also write some of the tests in Mocha testing framework. Going forward, we'll be also learning about PDAs, which are program-derived accounts, and also work a little bit on our front-end in TypeScript and Next.js to interact with our Solana program. As a result of that, we'll be building out our project, which will be your first proper Solana program, a Twitter clone with the tipping functionality. And we'll also write a proper testing in our own testing framework that we call Turnstile. So let's talk a little bit about the core concept of Solana. The app interacts with Solana cluster by sending in transactions with one or more instructions. The Solana runtime passes those instructions to program, and the programs are deployed by app developers beforehand. Instructions are then executed sequentially and automatically for each transaction. If any instruction is invalid, all of the account changes in the transactions are discarded. So some of you can spot an immediate or recognize some of the database aspects if you ever work with, for example, SQL databases. So if we talk about the Solana program, it is essentially a piece of code that is run by Solana blockchain. Programs in Solana are stateless, meaning that you can't store any data in them. This is a significant difference between smart contracts on Ethereum and programs on Solana, because, for example, if you're writing an Ethereum program, you can create variables, you can store some data directly in a smart contract. This does not hold true on Solana. On Solana, we have a clear distinction between accounts that are containing the program and accounts that are containing the user data. User data or a different account is then supplied to the program during the initialization of the execution. So essentially we use accounts to store both programs code, or what we call bytecode, and user data. We can definitely imagine them as separate files on the blockchain. So our first core concept is accounts. And there are three different kinds of accounts. We have data accounts that are used to store data. We have program accounts that are used to store executable or some form of executable payload or bytecode. And we have native accounts that indicates native programs on Solana that are a fundamental part of all the validators such as System, Stake, BPF Loader. So at the bottom we can see a bit of a visualization how different fields in the accounts look, and we'll be talking about each of them in detail later. So here is a clear distinction between Ethereum and Solana. If we have, for example, a really simple counter with increment and decrement feature, on Ethereum we have some form of smart contract account that contains data and some executable EVM bytecode. On the other hand, if we look at our Solana visualization, we have our program account that is executable and has some form of executable bytecode in the data, and we have a data account. And this data account contains some form of user data. And there is a clear distinction between the executable bytecode and the user data we're supplying to the program. Within those data accounts, there are also two types. One of them is system-owned accounts and PDA or program-derived address accounts. And each account is different in some form of way, and we'll be talking a little bit more about PDAs in our next lecture. So accounts can only be owned by programs. Owner of these accounts has a full autonomy over the owned accounts, and it is up to programs creator to limit this autonomy. and up to the users of the program to verify if the program's creator has really done so. So let's briefly talk about all the fields that are usually stored in the accounts in Solana. So the main is essentially a key, which is a pub key that is used to identify an account. It is 256-bit long, and it is usually a public key pair. Another one is a program owner, which is another pub key that indicates who's the owner of this account and the only account that can write the data into this account. Only the owner of the account may assign a new owner, and after it has been fully zeroed out, which means the data payload needs to be zeroed out before the owner assigns a new owner, essentially transferring the ownership of the account. Another important one is LAN ports. It is a number of LAN ports owned by this account, and only the owner of this account may subtract its LAN ports. Everyone can credit the account, which means we can send LAN ports to any account we want. But if we want to subtract this data or subtract the LAN ports or essentially spend them in any way, we need to be an owner of this account. And then obviously the data payload, which is essentially a raw data byte array stored by this account. It can be user data or it can be an executable payload. It is up to 10 megabytes of mutable storage and can only be written by the owner of the account and cannot be resized currently. So we also have some of the really important flags. One of them is a flag called executable, and it essentially marks if the account is executable during a deployment process. We mark that during a deployment process, and it tells the Solana blockchain that the data of this account is essentially a bytecode that Solana can execute. Executable accounts are fully immutable once they are marked as final. So essentially, if we deploy them, the data payload is not immutable in any way, and it is or they are owned by a BPF loader program. There is also something that is called rent, and storing data on accounts costs SOL to maintain, and it is funded by what we call rent. If you maintain a minimum balance equivalent to 2 years of rent payment in an account, your account will be exempt from paying rent. You can retrieve rent by closing the account. So essentially, if the account is no longer necessary, the owner can close this account, and it will send back the LAN ports back to your wallet. Rent is paid during 2 different timings, when it is referenced by transaction and once an epoch. Percentage of rent is collected by accounts, and the percentage of the rent collected by accounts is destroyed, while the rest is distributed to vote accounts at the end of every slot. If the account does not have enough to pay the rent, the account will be deallocated and the data will be removed. So essentially that tells us we have to maintain some form of balance to keep our account valid. So this introduced the concept of essentially quote-unquote garbage collection. So if some of the accounts does not have enough rent to be paid, it will be automatically deallocated, freeing up the space on the Solana blockchain. Another really important flag is signer flag, which essentially is indicating if the account has signed the transactions. It is not actually stored in the account, but it's just a runtime metadata. Another runtime metadata is writable flag, and it is indicating if the account is writable. So yeah, to tie all of this down, we have some of the 7 basic rules for Solana accounts. So first is each account has a unique address and a unique owner. Owner has a full autonomy over the owned accounts, and only the data's account's owner can modify its data and debit LAN ports. The program, as I mentioned, don't store any data. We have separate accounts for that, and accounts must pay rent to stay alive and not to be deallocated from Solana. Anyone is allowed to credit Lamport the data account, but if you want to spend them, you need to be the account owner. The owner of the account may assign a new owner if the account's data is zeroed out. So if you want to transfer the ownership of the account, we need to essentially erase the data contained in that particular account. Let's talk about transactions. The basic operational unit on Solana is called instruction. Instruction usually contains the program ID of the intended program we're calling, an array of all accounts we intend to read from or write to, which ties to our previous chapter about accounts. We're essentially supplying some form of user data to the called program, and the instruction data, which is a byte array that is specific to the intended program. So just like in any form of SQL databases, we can bundle multiple instructions into something that we call transaction. If we are forming transaction, we're essentially supplying an array of all accounts we intend to read or write to, one or more instructions, a recent block hash, this is really important, and one or more signatures for that particular transaction. We are also specifying a writable signer, which is the account that is serialized first and will be the fee payer for the whole transaction. So let's just talk a bit about the deep dive into the transactions. So the Solana runtime requires both instructions and transactions to specify the list of all accounts, which we can see right here. When the transaction is submitted to a cluster, the runtime will process this instruction in order and atomically. And for each instruction, the receiving program will interpret its data array and operate on its specific accounts that we're supplying. The program can obviously have two results. If it goes well, the whole transaction is submitted. On the other hand, if we got some form of error code and the error is returned, the entire transaction will fail immediately. So even though if we are doing multiple instructions and one of those instructions fails, the whole transaction is reverted. Any transaction that aims to debit an account or modify its data requires the signature of the specific account holder. Any account that will be modified is automatically marked as writable via the Solana runtime. An account can be credited without the holder's permission, so long as the transaction fee payer covers the necessary rent and transaction cost. Also, let's get back to a recent block hash. Before the submission, all of the transaction must reference the recent block hash for a very good reason. It is used to prevent duplications and eliminate the stale transaction. And for each transaction, the maximum age is about 150 blocks, which is about 1 minute 30 seconds. But that obviously varies as we go. But essentially, if the transaction is marked as stale or over its max age, it is automatically eliminated, not processed, and reverted back. So yeah, let's just sum it up. Instructions in one transaction are processed in order and atomically. If any part of the instruction fails, the entire transaction fails. We have some form of limit for a transaction, and to prevent the program from abusing the computational resources, each transaction is given a compute budget. There are 5 really important things that we need to know about transactions. We can think about this that all of the program inputs can be potentially malicious for a few reasons. Any user can obviously compose these transactions. That means it can be whatever instruction in the transaction, and user also provides all of the accounts. So what we need to do here from the developer's perspective, we need to check the signers, we need to check the owner, and we need to be beware of the unexpected order of instructions within the transaction. We also obviously need to cover any form of invalid input from a side of the user, and also think of the compute budget when we are designing these transactions in our program. So now that we know about accounts and transaction, let's just set up our first Anchor project. So let's just go ahead and create a new Anchor project. After we create our Anchor project, we'll just go briefly through different folders of our project and introduce what they mean in our project and how we'll be working with them. So I believe all of you have probably followed the instruction we have given in the lecture number 1, but if you didn't, please switch back to lecture number 1 and install all of the necessary tooling. In case you will have any issues with Yarn Package Manager, please install it using this command, because I believe that Anchor is using a Yarn Package Manager, and we have not mentioned that in our lecture number 1. However, when we're ready, something really similar to npm package manager in JavaScript or TypeScript, we can just go ahead and type Anchor in it and the name of our Solana program. Let's just call our Solana program Hello World, or for example Calculator. I'll call it Calculator because we'll be expanding our Hello World sample into a full calculator a little bit later. So right now the Anchor will initialize the whole project. It creates a new Anchor workspace you can move into after the initialization is complete. And there are some of the really important files in our project folder. So let's just go ahead and switch to our Calculator project. And now that we are in our project, we can see that we have a couple of files we need to talk about. A couple of interesting ones. We'll have an .anchor folder. This will include the most recent program logs, and also local ledger that we'll be using for testing. We have a app folder. App folder is essentially an empty folder that you can use to hold your front end. If we'll be using a mono repo to kind of host our full stack solution into one GitHub repository. So yeah, we'll be definitely using that later. We'll be creating a separate TypeScript or Next.js solution here in the app folder. We have a programs folder. This is the most interesting one for us. It's essentially the folder that will contain your Solana program. It can contain multiple programs, but initially we'll be just working with a single program. And we also have a test folder. And the test folder will be containing all of our tests developed in TypeScript using a Mocha testing framework. We also have a migrations folder. We can save our deploy and migration scripts for our program. And the really important one is anchor.toml. Anchor.toml is essentially the file that configures your whole workspace for your program. We also have a cargo.toml, which includes all of the packages we're using in our program's workspace. So now, when our Anchor workspace is all set up, let's just go ahead and open it up in our preferred IDE. I'll be using Visual Studio Code as mentioned in lecture number 1. And before we get into an actual code, let's just briefly talk about the whole development process. You can use different ways how to test out your program. I recommend you to run something that is called local ledger. This will essentially local ledger is basically a simulation of the Solana cluster inside your local machine. So when building locally, we don't actually want to send anything to the Solana blockchain. So this is exactly what we want. Unfortunately for us, running a local ledger is really easy. So before we actually run the local ledger, let's just set up our Solana CLI to talk with the local host or the local ledger. And we can do that by calling Solana config set URL to local ledger. So we'll be essentially using an RPC for our local ledger that will be running in a different terminal. So let's just set that up. We'll get a confirmation for our RPC URL and our WebSocket URL. It should be set to the local host. So, and yeah, before we actually run the ledger, let's just verify we have a key pair ready. So let's just call Solana address. And as you can see, I have my key pair already generated, but in case you don't have one, you can just run Solana keygen new as mentioned in lecture number 1. So now when our Solana CLI is talking with our local ledger, let's just spin one up. So we can do it by creating a new terminal instance. For example, I can just create a new one in our IDE. And after we are in our new terminal, let's just run command called solana-test-validator. This will initialize essentially a simulation of Solana on our local machine. You can notice that it will generate a folder that is called test-ledger. And this one essentially contains the state of your local ledger. So for example, if you stop your ledger and you resume it after you get back to your development, it will load up the state from this folder. But please be aware that the test ledger folder grows with time, obviously. So now that we are all set up with our local cluster, we can just verify that we have some SOL on our account by calling Solana balance. And as you can see, I have some SOL airdropped to my account from our local ledger. You'll probably have a lot of SOL there, so you're essentially good to go. But the whole development process is as follows. During your development, you'll be using a local validator to test out everything that you need. And when you're happy with your program, you can just essentially swap up your RPC, deploy it to the local net or a devnet or testnet, test it out there, and essentially invite other users to test out your program. And when you're happy with that, you can ship into a production by essentially deploying to the mainnet. Yeah, so now we're pretty much ready, and we just need to know a couple of commands, how we'll be working with stuff here. So before we'll be actually deploying the program, we need to compile it into a bytecode that is that can be interpreted by Solana runtime, and we can do that by calling anchor build. You can see a couple of errors, but that's not really interesting for us right now. During the first run, it will probably compile all of the dependencies, so it will take some time. But yeah, essentially you should be greeted with finished in some sort of time. But when you do your anchor build, you can then essentially deploy your program. So let's just run anchor deploy. And you can see that it's sending out 177 transactions to deploy our program. It will say deploy success, and you will get your program ID. So now when we completed our initial deployment and we get our program ID in the terminal, what we need to do right now is update our program ID in our workspace. So that's because before our initial deployment, we simply don't have any idea what will be the public address of our program after the deployment. So when we complete our initial deployment, let's just go ahead to our anchor.toml file. And you can see we have some form of pre-generated ID of our program. So let's just go ahead and replace it with our program ID from the deployment. Save that one. And we also need to update our ID in lib.rs, which is stored in the programs folder. And it's our entry point for our program. So yeah, let's just update that. And yeah, finally, we just need to build and deploy one more time and make sure that our program is compiled with the right identifier. So let's just run anchor build. So we're good, we're finished, and then we just run anchor deploy. Yeah, and now let's just verify that our program ID matches the program ID in our lib.rs and in our anchor.toml file. Let's just check out the script section. As you can see, we're defining a test script, and we can run all these test scripts using a command anchor run and the name of the command, which in our case will be pre-generated, and it will say test. It will be run through yarn, and it will execute all of the TypeScript files in our test folders. If you check out the test folder, you can see that Anchor already created a test for us that will check if the program is initialized. So yeah, we can just go ahead and run anchor run test. It will connect to our local validator, and as you can see, it's passing the initialization test. And you should get really familiar with this process because you'll be running tests a lot during the development, because the usual process is writing tests for all of your program's features before you actually get into writing the whole front end that will be interacting with your Solana program. We know how to work with our Anchor workspace. Let's jump back into the lib.rs file and try to or start working on our calculator. So let's just begin by with erasing some of the boilerplate code that the Anchor generated for us. Erase the account structure and the initialize function. And in our case, let's just create a new create function that will essentially just create a new instance of our Solana calculator. So we can do that by putting in pub fn, essentially what we know from our Rust lecture, and let's just call it create. And now for our function parameters, we need something that we will call context. Context in Anchor will essentially help us access the accounts that the user is supplying while calling this function. So yeah, let's just context of a type create. We'll get back to it a little bit later. It's really important. And now add init message. Init message will be just a string that we'll be fetching and then essentially setting the value of this init message to one of the accounts that the user is supplying to this function. And now we just need a return value for our function, which will be program result in case of Anchor. So yeah, we have created a skeleton for our create function, and our create function takes context. As all of you already know, Solana is stateless, so we have to supply all of the accounts that we want to work with. We will be accessing them using our context, and we're also having an init message parameter that will essentially take our string in our parameter and assign it to one of these accounts. So now if we want to access these accounts, let's just create a new variable. We'll call it calculator. Make it immutable because we'll be working with the data, assigning a new data to our accounts. And then we can just call ctx, which is our context, accounts, and the name of the account that we want to fetch. In our case, it's calculator. And now we have our account in our variable, and we want to set the value in some of the fields in our account. So we can just access it, calculator, just call it a greeting, and set it to our init message. So now we have assigned our init message to our greeting in our account, in our calculator account, and we need to let Solana know that the execution went through successfully and the function is complete essentially. And we can do it by calling an OK statement. OK statement with curly brackets inside of it. This will let the Solana runtime know that the function is essentially over and has successfully completed the execution. So now we know how to define a new function in Anchor, and we just need to know a little bit more about the context and how we'll be defining a structure of all of these accounts that we'll be working with. We have created our create function, and we need to dig a little bit deeper into the context. So context is essentially a list of accounts that the user will be supplying when invoking this function. And we can create our context by using a macro that is called derive. So let's just put in hashtag derive, and our context will be derived from accounts. Now we can just essentially define our context using a structure, just like we learned in our Rust lecture. So let's just do a public structure that we will call create. And now we can just put in all the fields that we want to have in our context. So first of the accounts that we are accessing in our function is the calculator account. So let's just add that one in. And it will be a type of account. And it will be a type of the calculator account. We'll obviously need to define that one later. The really important thing here is that we are trying to initialize our calculator account here. So the calculator account does not exist at the time of the invocation. So we need to specify that this account needs to be created or initialized. And we can do it by specifying another macro. And specifying the init. We want to initialize the account. We need to specify the pair for the initialization, will be, in our case, will be user. And we also need to specify an amount of space that our calculator will allocate. So let's just put like 264 in, but it's obviously recommended to calculate how much space your account will need to kind of save up on the space on Solana. So now the other accounts that we need is the user, which will be essentially the signer of the create function, and also the system program. So let's just define our pub user, which will be a type of signer. And we also need to reference the system program. We have already mentioned that in when we showed the account structure in this lecture. So we'll be referencing a program system. Yeah, so essentially that's how you define context for your function using a Rust structure. And now we need to go ahead and create our calculator account that we are referencing right here. So we can do it again by setting up a macro, hashtag account, and then leveraging Rust structures to define a structure for our calculator account. So let's just do public struct that we call calculator, and let's just put all the fields that we need inside our calculator account. So we are accessing the greeting inside our calculator here in the create function. So let's just add greeting in our calculator. It will be a type of string. And let's just also add result, which will be integer 64 in our case. And we'll be adding result into our calculator account because we'll be saving all of the results of the all operation that we will integrate inside our result inside the calculator account. So when the user does some form of application or some form of calculation using our Solana calculator, the result will be always saved inside the calculator account that he's owner of. Now we know how to create a function, an appropriate context for a function, and also how to define a structure for an account. So I have added another function to our calculator, which is essentially an addition function. And you can see that I'm following the same concept as before. Setting up a context, I've created an addition context, and I'm also letting users supply number 1 and number 2, both of them integer 64. And what I'm doing, I'm yet again accessing a calculator using a CTX accounts calculator, and then I'm adding it to a result, essentially adding these two numbers in our function parameters. After that, I'm saying to Solana runtime that the calculation went through and the function is essentially over. As you can see, I'm creating a separate context for our addition. for our add function that I called addition. If we take a look at the addition, the only account that we are supplying in our context here is the calculator. And as you can see, we are supplying a mutable account that is already created in our initialize function. So if user wants to access all of the features of our calculator, he needs to call the create function first to actually initialize his calculator account, pay for the initialization, and allocate all the space necessary for us to save all of the data from all the operation we're planning to do using our calculator. So now when we're happy with our implementation in the Solana program, we need some way to test out our implementation. Before we get into implementing a whole front end or deploying it to DevNet, testnet, or eventually into the mainnet, we have to write a proper test to test out all the functions. So we can do it using the internal testing framework in Anchor using the Mocha, and that is done by creating a TypeScript of testing scenarios. As I've shown before, Anchor is already pre-generating your testing scenario for the Hello World program that we shown before, but I have prepared a testing scenario for our calculator. So it works in a way of creating a pre-described collection of it blocks. So in this case, I've created a collection of tests, which I call calculator, which is aimed to test all of the functionality in our calculator program. Before we start defining any of the test it blocks, we have to set the provider for our test. In this case, we're setting up the provider to a local cluster that we're running on our computer. After that, we need to reference the program itself. This creates some form of abstraction that allows us to call methods in our sole program. So I'm doing that by creating a constant program and then referencing our workspace name, which is calculator in this case. After we have a reference to our program, we need to start generating a key pair for our calculator account. As I said before, we have our calculator account that is storing the greetings message and the result for all the operation we're doing with our calculator. So yeah, we obviously need to generate the key pair because we'll be interacting with the same calculator account in different testing scenarios or different test it blocks. After that, I'm just creating a constant text that I'll be using in our create function to store it inside the calculator account. So after we have all of this ready, we're pretty much set to define all of our it testing blocks. The first test blocks that I'm creating is a test block that will verify our create function. So I'm calling it a creating calculator instance. So then we can use program methods to call different methods in our program. So we're essentially referencing the program we did here before at the line 13. So now you can see I'm calling the method create and I'm supplying my text, which is expected because we expect user to send out some initialization message here in the function parameters. And we also need to supply all of the accounts we want to fit into the context of our create function. So we are adding our calculator, which is using the calculator pair or the key pair that we have generated before. We're also referencing the user, which is the public key of the wallet that is interacting with the test, and also referencing the system program using the system program.program ID, which is a constant directly in the testing framework. After that, we're also specifying all of the signers, which in this case is the calculator pair. Then using the RPC method, this will send out this will essentially call out function in the Solana program using an RPC, in this case, using an RPC to a local host. After we successfully call this function, we need some form of verification if everything went okay. So
We are doing that by fetching our calculator account back. So yet again, we're using the calculator pair public key we have generated before to fetch the contents of the particular account. After we have the content of the particular account, we can use the expect functionality to kind of compare the two different values. In our case, we're comparing the content of our account, which is the greeting. If it's equal to the text we have sent out before using our RPC to our program. If this condition is met, then the test it block passes. However, if these two values are not equal, then the whole test block fails. So after we test out our creating of a calculator instance, we're going up to another it block, which is a different test, and all these tests will be executed in order. So right now we're testing addition function. So I'm essentially doing the same thing as in the previous it block, but instead of calling the create function, I'm calling the add function we have defined in our program. In this case, we're not expecting string, but we're expecting two different integer 64 numbers. So as you can see, I'm passing out two numbers using anchor bn. So we have a number 2 and number 3, which essentially means if we call this function with number 2 and 3, an expected output should be 5, and that should be stored in our calculator account. We're also supplying accounts for our context for the add functionality, which in our case is just a calculator account that we have generated in the previous step. So yet again, I'm passing the calculator pair public key as our kind of calculator account that we'll be writing our result into. Yet again, I'm executing the function using our RPC, and then doing the same thing as before, fetching the account data back, and checking if the expected result is equal to 5 or 6. In our case, it should be 5 if you want to pass the test. Now, when we're happy with our test, it's the same situation as before. We're just trying to run anchor run test, and it will run throughout all of the test blocks we have defined in our TypeScript. So now we can see that a creating calculator instance went okay, and the addition was the same result, and it went okay too. But for example, if you want to demonstrate how the failing test work, we have addition of two numbers, 2 and 3, and let's just say we expect an output of 6, which is obviously wrong, and it will result in a failed test. So if I try to execute the test right now, our first it block passes, essentially creating a new calculator instance, but when we're trying to test the addition, it will start to fail. Why? Because in our case, the expected output is 6. However, the program works correctly and stores number 5 in the account data. And we can see it right here. The expected output should be 6, but the actual output was 5. So this is essentially how we can very easily define different test blocks to test out if our program implementation on Solana blockchain is correct. So after we're happy with all of our tests, let's just say we switch it back to 5, and we run the test again, and all of the tests are passing, then we can switch up from our local test validator to, for example, testnet and devnet, and deploy the program there. When we're happy with the functionality on the devnet or testnet, we're good to go into the production and deploy the game on the mainnet. So if you're interested in exploring these test scenarios even further, I'll be sharing my GitHub repo with all the calculator and tests. And you can try to add your own functionality into the calculator, for example, multiplication, stuff like that, and then write appropriate tests for these functions too. But essentially, you'll be just doing the same thing all over again. Instead of just executing addition, you'll be just multiplying two different numbers. Checking out lecture 3 in Solana, or Winter School of Solana. I hope you learned something about how to implement basic calculator program on Solana blockchain. That's why I started doing calculator in the previous lecture. I kind of wanted you to see the difference between raw Rust implementation outside of Solana and porting out the same program to a Solana blockchain. Also, don't forget to uh, check out the task for this lecture. We'll be asking you to implement more functionality into our calculator sample that you can get on our GitHub. And after you're happy with your program, don't forget to submit it at the end of the Sunday of this week. Um, Starting next week, we'll be doing a little bit more complicated program. We'll be implementing our own Twitter clone using Solana. We'll be also talking a little bit about PDA accounts. And yeah, that pretty much ties down to our lecture about the introduction into a Solana programming model. And I hope to see all of you next week. And if you have any feedback on our lecture, please don't forget to submit it using our Google form. Thank you again, and see you next time.